Hello, in this video we're gonna see different proof techniques, and usually we prove result about specific subject. Such result need not to be universally true, and we can introduce hypotheses that are true only in its domain. We've seen this in the previous sections. So proof can be much more controversial as long as they can be backed by some formal logic or justifications. So we've seen inductive reasoning in the other section. This is where we draw a conclusion from a hypothesis based on experience, and hence the more cases you find where P follows from Q, the more confident you are about the educated guess that if P then Q. And deductive reasoning, here we find a counterexample that disprove the educated guess, or either prove or disprove this conjecture. So that's what deductive reasoning. So where we've seen before in the previous chapter, we've seen inductive reasoning, and now we're gonna see some deductive reasoning. Some examples for here, we have deductive reasoning will be a counterexample. So when you apply this deductive reasoning, you try to verify the truth or falsity of your educated guess. So you produce a proof of if P then Q, thus making it a theorem. So all theorems are already proven. It's usually if P then Q, or if P, or P even only if Q. These are theorems, so usually they are already proven. That's why we call it a theorem. Or else you find a counterexample that disprove the conjecture. So either you're gonna prove or disprove something. So to disprove something, you just need a counterexample. So here it says prove that for every positive integer n factorial is less than or equal to n squared. So okay. So by trying n equal 1, this is equivalent to 1 is less than or equal to 1, we're good here. How about 2 factorial? Is 2 factorial less than or equal to square? So you have 2 less than 4, we are good. How about 3 factorial? Is it less than 3 square? So let's see, we have 3 factorial, that's 1 times 2 times 3. Which is 1 times 2 times 3, which is 6. And 3 squared is 9. So 6 is still less than 9. We are good. So it looks like it's true. But if we jump to 4, let's see. Is 4 factorial less than or equal 4 squared? Well, 4 factorial is 1 times 2 times 3 times 4. So that gives me 24. But 4 squared is only 16. So here I would say no. So this is the counterexample. When we get n factorial equal 24 and n squared 16, so we have a counterexample to this theorem here that says for every positive integer n factorial is less than n squared. So even finding a single case that does not satisfy the implication is enough to disprove the conjecture. So this educated guess that's stating that n factorial is less than n squared for all n positive integer, here we have a counterexample that shows that that's not true. So once you have the counterexample, what does it mean? That if for all positive integer greater than or equal to 4, so more example here for this counterexample. In general, if we say all animals living in the ocean are fish, we're gonna say, well, how about a whale? Whale is a mammal, so it's not a fish. Or if we have every integer less than 10 is bigger than 5, how about when the integer is 4? So here we have a counterexample, the integer 4. It doesn't work for every integer less than 10 is bigger than 5. So 4, it's not bigger than 5. Okay, so what we're gonna see in this section, we're gonna see that if we cannot disprove a conjecture by finding a counterexample, then we try to prove it using this method, either proof by exhaustion, as we're going to see a few examples there, direct proof, proof by contraposition, and proof by contradiction, and of course serendipity. So if leading with finite domain in which the conjecture to be shown true, then using the exhaustive proof technique, one can go over all possible cases for each member of the finite domain. So the key here for exhaustive proof is to have finite domain. And sometimes you let the computer do the work, you write a program to do all the exhaustive search and find you the result that it works. So this is only for finite domain. So this example, for any positive integer less than or equal to 5, so if n less than or equal to 5, the square of the integer is less than or equal to the sum of 10 plus 5 times the integer. So here we try 0. 0 square is 0. 10 plus 5 times 0 is 10. And 0 square is 0 square less than 10. Yes. And so the same way we try 1. And then we could see that 1 is less than 15 and we say yes. You try 2 and we're gonna say yes. And we try 3. 3 squared is 9. So 9 less than 25, yes. So for 4 it works as well. And 5 also for 5. So this is the exhaustive proof. We tried all cases less than or equal to 5 and we found it works. So we could say this conjecture is true. We're done. Let's see another example here. It says if an integer between 1 and 20 is divisible by 6, then it's going to be divisible by 3. So what we do here is 0 to 20 that are divisible by 6. So I wrote all the numbers here, but I didn't write all the way to 20, so you could keep going until you get to 18 and then get to 20. So as we see, these are all no. But 6 is divisible by 6 because 6 over 6 is 1. 12 divided by 6 is 2. Then 18 is divisible by 6 because 6 times 3 is 8. So now we get all divisible by 6. Now you're going to try. It says if divisible by 6, it is also divisible by 3. Well, is 6 divisible by 3? Yes, because 3 times 2 gives me 6. So 12 is divisible by 6 and it's also divisible by 3. And 18 is divisible by 6, but it's also divisible by 3. And now we did an exhaustive proof. That means we tried all the numbers less than 20 and we'll find out that if those numbers divisible by 6, they're going to be divisible by 3. So simple as this. This is the proof by exhaustion, only for limited number in the domain, when the domain is finite. Let's see other proof, which is direct proof. So we've seen some of this direct proof in the past. So a direct proof of P implies Q is used when exhaustive proof does not apply. When you cannot check every member of the domain, then you're going to use direct proof. So what does it mean? You assume the hypothesis P is true and you prove the conclusion from the hypothesis. So that's what we've seen in all chapter 1. So prove the conjecture x is an even integer and y is even integer. If this is true, then the product x times y is even integer. So here we could use direct proof as we've seen in the previous section. So what we're going to do, we write down the hypothesis. X is even integer, y is even integer. And then number fact, this is by definition of even number. If x is even, then there exists a case such that k is integer and x is equal to 2k. And then you can do universal instantiation, where x is even implies there exists k. K is integer and x equal to k. And the same with the y, we use the same thing for the y because y is even. and so on. So, and then you get some MP, and then m is an integer, and x equal to 2m, and so on and so forth. So this proof can be long because this is a formal proof, but we don't need this. It's hardly be needed. So instead I will show a different proof, a direct proof, but it's a little bit simpler. So what we do, we're gonna let x equal to m and y equal to n, and I would have to say where m and n are integers, because that's what does it mean, x even and y even. If x is even, that means it's equal to 2m, where m is any integer, and y is even if y equal to times some integer n. And then this is the hypothesis. Then x times y is equal to 2m times 2n. Or I could say it's 2 times 2mn. I just move the 2 using the associative property. So where I could say that 2mn is integer, because m integer, n integer, and 2 is integer, therefore the whole product is an integer. And that's it. Now we could make a conclude thus, if xy can be written as 2 times some integer, that means xy is even. xy, x times y, has the form 2k, where k is integer, and therefore xy is even. So this is simpler way of proving if you multiply 2 even, then the product is as well even. So this is called direct proof, but different than the formal proof that I showed you earlier.